Andrei Maltsov from Landau Institute. It's the second speaker from this famous institute. And more important, that he is a student of Sergei Novikov, his supervisor, and the persons who survive under Novikov's training becomes very serious scientists. So I guess this is enough to say about Andrei Maltsov. So please.
Thank you. I'm very grateful for inviting me here. So I'm going to speak about the geometry and topology of the Fermi surfaces in metals and the dependence of the Haloana magnetic phenomena in strong magnetic fields on the Fermi surface and on the direction of the magnetic field. So first of all, let me say that everybody knows that the electron states in crystal, for example in metal, can be enumerated by the conductivity zone, conductivity band, yes, and some number which is called quasi-momentum, and this quasi-momentum is not a vector, but it belongs to the three-dimensional torus, or you can say that it belongs to the Euclidean space R3, which was factored by the reciprocal lattice vectors. And Fermi surface is a surface in three-dimensional torus, or a periodic surface in three-dimensional Euclidean space, which is given by the equation epsilon of p is equal to epsilon Fermi, which is where epsilon of p is the dispersion relation. So the energy in crystal for a fixed conductivity zone is a function of the quasi-momentum, and this is a smooth function in three-dimensional torus, yes, or a periodic function in the Euclidean space, in p space. Yes, and so what we are going to consider, the influence of the geometry of the Fermi surface to the conductivity phenomena for other strong magnetic fields. So first of all, let me say that after we made a quantization of electron states in crystal, yes, and we parameterize all electron states by the energy band number and the quasi-momentum, we can consider the electron motion in crystal in p space quasi-classically. So we just use the dispersion relation on three-dimensional torus, which arises from the quantum picture. Yes, and after that, for the external fields, electromagnetic field, we can use the quasi-classical approximation, and in this case, we can say that the quantum states of electron in crystal, in metal, for example, is governed by the quasi-classical system, which is written for p in p space, and is given by the system which is similar to Lorentz system in the R space. Yes, so here on the picture we just write the evolution of quantum states of electron in p space under the action of a magnetic field. So we apply just first the rather strong magnetic field. What means strong, I will say a little bit later. So let me first say that the approach, this topic was actually started in the school of Ilya Lifshitz with his pupils, who were very interested in the influence of the geometry of the Fermi surface and the geometry of the corresponding electron trajectories to the conductivity phenomena. So we can see here that the quasi-classical electron motion, well, this actually the motion in p spaces, is governed by some dynamical system in three-dimensional torus. So we can ask about the electron trajectories in p space given by this system in three-dimensional torus. So first of all, what can we see? First of all, we can see that there is an integral of motion for this system, and this integral of motion is given by the energy of the electron, or actually of the quasi-particle in three-dimensional torus. And actually there is another integral of motion which is given by the projection of p on the direction of b. Yes, if you consider this system in three-dimensional space and you consider all the functions to be just three periodic functions, you can say that you have two integrals of motion. Yes, and you can find analytically the trajectories of electrons. analytically, these trajectories are given by the intersections of the planes orthogonal to B and the constant surfaces of constant energy here. So if you put epsilon of P equals constant, yes, and take the plane orthogonal to B, then what you can see in the intersection is a three-dimensional is a electron trajectory in a three-dimensional space. Yes?
B is dependent on P.
No, B is an external magnetic field. It can depend on coordinates, but here B is
given.
B is given, yes, and a constant vector.
Constant.
I missed, you said there's an integral. Can you write it down, the integral?
Yes, if you look at this system, yes, then it is easy to see that, first of all,
Another one.
you have this conservation law. Yes, const. This is the first one, and also if B is directed to z-axis, yes,
Yeah.
then PZ is also a conservation law. So in three-dimensional space. So you can say that analytically this system is integrable. But if you consider it in three-dimensional space, then you cannot apply this Liouville theorem or something like this, because you consider a system in the non-compact space. Yes. If you now go to the three-dimensional torus, which is compact, in this case PZ is not a conservation law anymore, because now PZ is not a function on three-dimensional torus, but you have only one form, dpz. Yes, the integrals of dpz over the one-dimensional cycles are not zero. So in this case, there is also some problem, I would say. So locally, analytically, you can find the trajectories, but the geometry of these trajectories can be still rather non-trivial. And actually, it is this geometry which affects the Galvano magnetic phenomena very much in rather strong magnetic fields. So, first of all, let me maybe first show. We can imagine very simple example. Yes, for example, here, the three-dimensional space. If you consider the three-dimensional space, we can imagine the Fermi surface as a three-periodic surface. For example, if the Fermi surface is simple, for example, you have a sphere. Or this means actually that you have a periodic set of spheres in three-dimensional space, or you can imagine this sphere embedded in three-dimensional torus. Then you can see that trajectories are always very simple. You have the compact electron trajectories always, and this situation is not different from the free particle consideration. Yes, for free particles where the dispersion law is very simple, p squared. You can always a sphere as a Fermi surface, yes, and you can always have only compact trajectories in the planes orthogonal to B in P space. Yes, if you consider the trajectory in R space, if you consider electron quasi-classically, yes, and you can consider both the P and R representation of the trajectory, then in this case, the trajectory in R space is a little bit more complicated than the trajectory in P space. So the trajectory in P space is flat, yes, but in R space, the projection of the trajectory on the plane orthogonal to B looks like the trajectory in the P space, rotated by pi over 2, but it can also have oscillations along the z-axis in R space, because there is a third component of the group velocity, yes, so the motion along B is allowed in strong magnetic fields here, I mean, in simple cases. So another simple example of the Fermi surface is periodic cylinder. Yes, so this is actually a set of.
The sphere corresponds to epsilon equal p squared.
For example, but also in many metals where you have simple dispersion relations, simple Fermi surface, like alkali metals, yes, you can have Fermi surface which is still sphere. And you can approximate epsilon of p by p over squared and p squared over 2.
Function of p squared.
Not actually a function of p squared, because in crystal it is not, there is no rotational symmetry, yes, but I mean approximately for alkali atoms. It is not very important for us, only topology of the Fermi surface will be important. Yes, but in the second simple example, still you can have also non-compact trajectories. Yes, if the direction of B is oriented in the special way, then in this case you can have periodic trajectories in R space, or you can imagine them in torus T3, but they will be closed there, but they will be non-homologous to zero. Yes, they will represent a non-trivial cycle, which is important. I mean, for physical applications, it is more convenient to imagine everything in three-dimensional space, but assume that everything is periodic. Yes. So what we can
ask a question?
Yes?
In the first example,
Yes.
is the sphere, does it lie entirely in a unit cell of the
Yes.
fundamental domain?
Yes. For example, it can lie entire in the elementary Brillouin zone. Yes, but it is
That
not
would be
very
boring.
important
What
here.
happens when what happens when it's bigger than that?
Well, first of all, the volume of the sphere cannot be bigger than the volume of the elementary cell. Yes, but geometrically, topologically can be very deformed sphere. Yes, geometrically, you can take elementary cell first of all in different ways. Yes, so geometrically it can be still complicated. I mean, if you just consider abstract potentials, abstract periodic lattices, what can be said if you have topological sphere? Its volume does not exceed the volume of the elementary cell. Yes, but its form, what will be important for us, that topologically it's a sphere, and that is all. Yes. I don't know if it is a theorem. If you can always, I think it is possible to, for abstract three periodic surfaces, it is possible to construct a counterexample. I mean, when you have a three periodic set of topological spheres, very deformed, such that you cannot choose the elementary cell in such a way that every component will lie in this parallelepiped. But this is not important at all. Yes, usually for alkali atoms, it is in one elementary cell, but it is not important.
If that's right, then if you could have that, then you'd have to have self-intersections, wouldn't you, if you have the copies?
No, we are going to consider Fermi surface without self-intersections. Yes. Let me not. I mean, there are some effects which are connected with self-intersections, but well, first of all, the self-intersection of Fermi surface is not a generic situation, because if you have a generic dispersion law, there will be no self-intersections. They usually arise from some additional symmetries. Yes, and it is actually destroyed in strong magnetic fields. Usually, you have this magnetic breakdown. So actually, for strong, let us consider non-self-intersecting magnetic fields and not self-intersecting Fermi surfaces, and this will be important actually for topological results we are going to consider. We can discuss a little bit self-intersecting pictures. So what is important, it was pointed out by Lifshitz and Asbel, Kaganov, Pishansky, that the contribution to the magnetic conductivity of these two different cases is different. Yes. What I mean magnetic conductivity. First of all, we consider the magnetic field. Yes, if we apply a magnetic field, there is no current. Yes, no current arises. But after that, if we apply a weak electric field to measure the conductivity in the presence of a strong magnetic field, the presence of magnetic field will affect the electric conductivity. So it does not produce the electric field itself, but it affects how the system reacts on the appearance of electric field. So let me show here the contributions of two different types of the trajectories to the magnetic conductivity tensor. So first, if we have only compact trajectories, yes, and we have z directed along B, then for magnetic field directed along B and magnetic field going to infinity, we can represent the corresponding conductivity tensor, its dependence on B, in this form, number 2. Yes, so tau here is the mean free time of electron. So actually what now I can say what means strong magnetic field. This means that the magnetic field is so strong that the mean free time is much bigger than the cyclotron, the inverse cyclotron frequency, yes? And geometrically this is very clear why it is important for the revealing of the trajectory of electron in p space, yes? Because in kinetic equation it is important. So if you consider the p space, yes, and in p space you consider the quasi-classical electron trajectory, the electron in p space moves along the trajectory, yes, and sometimes you have the scattering x, yes. So you can ask what is that part of the trajectory, its length, between the two scattering x. If it is much bigger than the Brillouin zone, yes, then you can say that electron feels the geometry of trajectory, the kinetic equation feels the geometry of electron trajectories, and in this case the geometry of electron trajectories will be important for kinetic effects. If it is much smaller, yes, like here, much smaller than if the mean free time of electron is much smaller than the inverse cyclotron energy, then electron will be scattered many times, yes, before it feels the geometry of the trajectory. And in this case, actually, the geometry of trajectories will not be important for the Halovan magnetic phenomena in magnetic field. So here, from this point of view, we can see the strong magnetic fields. This means that the mean free path of the motion of electron in p space is so fast, yes, that the geometry of trajectory is revealed between two scattering acts of electron. Yes. So in the first, yes.
Remember what is a strong magnetic field? 1 Tesla, 2 Tesla.
1 Tesla. Well, in experiments, if you consider rather pure metals, yes, the first experiments were made for 1 Tesla. But this is a specially made metal, which is very pure, yes, and at very low temperatures, like 4 kelvins. And in this case, 1 Tesla is enough to reveal the geometry of trajectories. Yes. So we can see here that for omega b tau going to infinity, in the plane orthogonal to b, we have the suppression of the conductivity in the plane orthogonal to b, and the conductivity along the magnetic field is allowed. Yes, it remains finite for strong magnetic fields, which is like in the classical picture. Yes, because you know in the classical picture, first of all, in the magnetic field, the electron makes a cyclotron motion, and after that, if you apply an electric field, then you can consider a drift of the center of the cyclotron orbit, and actually it is orthogonal to electric field. And actually here we can also see here that the first small term in the plane orthogonal to b is actually this cross conductivity sigma xy, yes, and the conductivity along the electric field is smaller. Yes, it is like 1 over b squared, and the conductivity along b remains finite in this situation. If you consider periodic trajectories, yes, in this case you have different picture, and this picture is rather different from free particle picture. So first of all, along b the conductivity remains finite, but in the plane orthogonal to b there are two different directions. The conductivity reveals strong anisotropy. In one direction, conductivity remains finite, yes, but in orthogonal direction, conductivity disappear for rather big magnetic fields. So the general form in three-dimensional space of conductivity is represented here. The picture is also clear because this means actually that in this situation the magnetic field cannot produce cyclotron orbits in three-dimensional space because the lattice potential is much stronger than the magnetic field. So the quasi-classical trajectory remains like a periodic line in p space and in three-dimensional space, and this means actually that it can be easily shown from the kinetic equation that in the direction corresponding to the mean direction of electron trajectory in X space, conductivity remains finite. Yes. Let me say now that actually at the same time, by the school of Lifshitz, also more complicated trajectories than just the periodic trajectories were discussed. They actually look very similar to periodic trajectories, and they produce more or less the same contribution to the conductivity for strong magnetic fields. So let me show just, so the trajectory is not periodic, but still it looks like a periodic trajectory. But let me just say some words before, because now I am going to consider some topological terminology, and this topological terminology is actually appeared later when Novikov posed this problem about the general behavior of electron trajectories of the quasi-classical system, which we considered at the first page. Yes, so now we can ask the general question. If we have a dispersion relation in three-dimensional torus with arbitrary smooth function, and we consider arbitrary irrational direction of the magnetic field, then what can we get for the geometry of electron trajectories? First, we can have compact trajectories, and okay, we can say in this case the geometry is known for us. But as we saw already, we can have open trajectories, and here the direction of B is special. But what if the direction of B is just arbitrary direction, and you have arbitrary three-dimensional picture in periodic picture in P space, and you fix any rational direction of the magnetic field? What can be the geometry of open electron trajectories on these three periodic surfaces? Geometrically, this problem is very, posed very elementary, yes? But it appeared, the problem was investigated at Novikov topological seminar, and I will say the names of people who actually made very strong topological investigation of this problem. But first, let me say some words about the approach, how to classify open trajectories on these three periodic surfaces. And what is the approach? And the basis, the basis of the topological investigation of this problem was made by Novikov conjecture. So Novikov conjectured that first the trajectories can be rather complicated, but generically, this means if you have generic Fermi surface for generic dispersion relation and generic direction of the magnetic field, in this case, the trajectory should be topologically regular. This means that the trajectory is not periodic. We cannot have periodic trajectories for the irrational directions of B, yes? But still it lies in the straight strip of the finite width and passes through it from one to another. So this behavior of trajectories was called topologically regular.
What does regular mean? It stays in a bounded neighborhood of an irrational direction in the R3?
Yes, you fix the three-dimensional surface. You fix the direction of B. You look what you have in the plane orthogonal to B. Fix any plane orthogonal to B. Look at the trajectories. So topologically regular means that any open trajectory, non-closed, is, deformed straight line. So there is always a straight line of finite width, such that the trajectory is lies entire in this,
so
and passes,
yeah,
but it is not periodic.
Oh, yeah, no, I understand. It's a bounded distance from an irrational direction in R3. Yeah, so it, right. Yeah.
So this was called topologically regular. And the trajectory of Novikov was Uh, okay, the conjecture note was, as I said, that for generic Fermi surfaces and generic directions of the magnetic field, you can have only topologically regular open trajectories. Yes. So the conjecture is rather non-trivial. Yes, because if you look at this complicated picture, you cannot say in advance what you are going to have in the intersection. And actually, there are some exams where you have more complicated electron trajectories. But let me say now some words about the results obtained by Novikov pupils. And the first was Zorich, who actually proved Novikov conjecture for small disturbations of rational directions of B. What does it mean? That even for complicated Fermi surfaces, if the direction of B is rational, then all open trajectories are periodic. Yes? Because the picture in the plane orthogonal to B is periodic, has two periods, and this means that all the trajectories are periodic or compact, and all the open trajectories are periodic in this case. So what Zorich proved actually, that if you have a small rotations, if you fix a rational direction of B and then make small rotations, in this case, the trajectories remain topologically regular. They are not periodic anymore, but still they remain topologically regular. More or less at the same time, Tsarev constructed an example of a trajectory which is not topologically regular. He invented the trajectory which is open in the plane orthogonal to B, but does not lie in any finite strip or finite width. So more complicated trajectories are possible. But this trajectory appeared to be non-stable. For example, it is unstable with respect to small rotations of the direction of B. Yes, and the final, I would say, the final big contribution was made by Dynnikov, who actually proved Novikov conjecture in the form how it was posed. So there was a set of series of works of Dynnikov, and now it is proved that for generic Fermi surface energy, the number of directions of B where you can have topologically non-regular trajectories is equal to 0.
Your Fermi surface is always triply periodic, though. You're assuming that?
Yes, Fermi surface is always, yes.
Triply
always
periodic.
triply periodic, always.
That's what the quasi-period result. You can do
I
it.
just guess because there are these examples, obviously, that are quasi-periodic surfaces, the ones that come from.
No. Fermi surface is periodic. But if you fix a irrational direction of B, yes, and look at the picture in the plane orthogonal to B, it is quasi-periodic, not periodic. Yes. Okay. So
It in higher dimensions.
let me now formulate the topological results in the form how they are formulated now after all investigations. Yes. Let me formulate the.
Excuse me, before you show the result, is it possible to see example of topologically non-regular? Can you show the picture?
Well, I will show later, but well, yes, it will be possible. Okay. So first, now let us fix the Fermi surface, which is a 3-periodic surface in R3, actually in P space, and consider all possible directions of B. So we can consider the unit sphere parameterizing the directions of B. Yes. So first of all, what can we see on this angular diagram? Which kind of electron trajectories? First of all, we can separate the regions where we have only closed trajectories. This situation is possible. For example, here you can have a non-trivial Fermi surface, but still for some directions of B, all trajectories are compact trajectories. So even for non-trivial complicated Fermi surfaces, we can see the regions on the unit sphere for which we can only close trajectories. And this will not be very interesting for us. We can say that everything is known here. Yes, the behavior of conductivity, the behavior of trajectory, more or less it is trivial. After that, we can claim the following thing. For some directions of B, we can have open trajectories on the Fermi surface. First of all, if we consider the trajectories which are stable with respect to small rotations of B, then all these trajectories are topologically regular. So if you have a situation, you have open trajectories, but still the situation is stable on the unit sphere with respect to small rotations of B, you can say that the picture is more or less simple. All the trajectories are still topologically regular. In some sense, they remain periodic trajectories, and their contribution to the conductivity tensor coincides with the conductivity tensor written down by Lifshitz and Pishansky. So you have almost nothing new except one thing. Actually, this is the place where topological numbers in conductivity arise. So let me explain what mean topological numbers in conductivity. First of all, if you fix an irrational direction of B, I mean, there are many topological numbers in conductivity, like in quantum Hall, yes, but here this will mean different thing. So first, if you fix an irrational direction of B, you will have topologically regular trajectories in the planes orthogonal to B. Their direction is irrational because the plane orthogonal to B generically does not contain rational vectors at all. Rational means integral linear combination of the reciprocal lattice vectors, yes. But it appears that the directions of topologically regular trajectories are always given by the planes orthogonal to B and some integral planes in three-dimensional space. Integral plane means the plane generated by two reciprocal lattice vectors. And this plane is stable with respect to small rotations to B. So, rotations of B. So, this means actually that we can also separate the regions on the unit sphere where we have topologically regular open trajectories. These trajectories exist for some actually regions on the unit sphere with piecewise smooth boundary, and for every stability zone, stability region on the unit sphere, we can introduce some integral plane, which can be rather non-trivial. Maybe for rather complicated dispersion relations, this can be an integral plane given by three rather big integers, and these topological numbers can be extracted from the conductivity observations in the plane of orthogonal to B. So if you fix this situation for the given direction of B, and after that you observe a stability zone, you rotate the direction of B, and you find the anisotropy of the conductivity tensor in the plane orthogonal to B. You look at the direction of the smallest conductivity, yes, and you can claim that for this stability zone, this direction always belongs to some integral plane in P space. Yes, so this is another generic situation. So we consider it now just two generic situations. One is just closed trajectories, and another stable open trajectories. In R space, let me say that in R space, the direction of this two-dimensional plane in three-dimensional space in R space can be given by this equation. You have to use this color.
Yes? So you seem to be saying that having compact trajectories is an open condition with respect to changes.
Yes.
I would think if it's just a torus, you're going from rational. Oh yeah, I'm sorry, I see that.
Yes, you are right. The regions on the unit sphere which contain only closed trajectories, this is an open set on the unit sphere because it's an open property. And if you consider these topologically regular trajectories, yes, for example, stability zones, then every stability zone is a closed set on the unit sphere. Actually, this region on the unit sphere with piecewise smooth boundary. Yes. Now, non-generic cases. For some directions of B, we can have open trajectories which are more complicated than, oh, sorry, in another direction. Which are more complicated than these topologically regular trajectories. So, just some points on the unit sphere are shown. This means that for these points we have the directions of B where we have more complicated trajectories. So first of all, I already mentioned Tsarev trajectory, which is actually more complicated than topologically regular trajectories, but not very much. This means that it still has the asymptotic direction. It does not lie in any finite strip of finite width, but still it has an asymptotic direction, and its contribution to the conductivity tensor is more or less similar to the contribution of topologically regular trajectories. But, and in this case, the direction of B has irrationality too. But for strictly irrational directions of B, there was another example constructed by Dynnikov, and Dynnikov proved that for rather complicated Fermi surfaces, you can have open trajectories which are rather chaotic. So they walk over all the plane orthogonal to B, and these trajectories are very interesting. For example, if you ask about the Fermi surface, yes, then there is a theorem of existence for other complicated Fermi surfaces. These trajectories always exist for some directions of B. For example, there are a lot of such examples for the trajectory for the Fermi surface given by this very simple analytic dispersion relation. If you consider, for example, this, it looks very simple, but it is very rich from the point of view of this dynamical system. So for this Fermi surface, you can observe all possible cases which are just allowed.
In what sense are you using the word chaotic here?
What?
Chaotic.
Chaotic. Well, this is topological terminology because actually, if you consider the situation in three-dimensional torus, yes, then it appeared. Because, you know, in the theory of integrable systems, you usually call the system integrable if the trajectories cover just tori of half dimension, yes? They are quasi-periodic, something like this. And all other situations are called chaotic, non-integrable, and so on. So if you look at these trajectories in three-dimensional torus, you can actually introduce some kind of topological integrability. So if you look at the Fermi surface, and if you look at the pieces covered by the corresponding trajectories, then actually for topologically regular trajectories, you will have the closure of these topologically regular trajectories represent actually two-dimensional tori with holes. This is not actually two-dimensional tori, but it is still two-dimensional tori with holes, such that, for example, a piece of surface, the hole is actually absent in the surface, yes, and the trajectories behave something like this sometimes, but still they cover two-dimensional tori. And this trajectory covers more complicated surfaces.
Trajectory through every point of this train.
No, this in the plane orthogonal to B, this is a level curve epsilon of P equals const, yes?
Yeah.
So,
if I change the constant, you get another.
Well, now, if you change the constant, this actually was the first consideration of Dynnikov. This trajectory, I will say later, they exist only at one energy level. The topologically regular trajectories, they exist in some energy interval. They are stable, both with respect to rotations of B and with respect to small variations of the Fermi energy. This trajectory is unstable, both with respect to the rotations of B, and it is unstable with respect to small variations of the Fermi level. So if you just take the energy a little bit less than the Fermi energy, all trajectories will be closed, and they will be like electron type, yes? But if you take an energy level a little bit above of the Fermi energy level, all trajectories will be closed, but they will represent the whole type electron trajectories, yes? So the whole conductivity will be like the conductivity made by positively charged particles. I mean, if you want to consider as free particles, yes. But yes, this trajectory exists only at one energy levels.
If you change the constant in a continuous way,
Yes.
the picture will
Yes.
change in a continuous way as well.
No, because, well, if you consider, what do you mean continuous? Yes, if you consider epsilon of p equals epsilon Fermi minus delta epsilon, yes, where delta epsilon is small but finite, yes, then this trajectory is constructed in such a way that it is non-compact and it is quasi-periodic, and there are always points where trajectories comes to itself very closely, something like this, yes.
Yes, but
It does not intersect each other.
As epsilon goes to zero, at the moment epsilon
Yes.
equals zero, you have the jump in topology.
But for a long time, so it's a trajectory. So if epsilon is small, it looks like this for a long time, but then it diverges from this. That's the essential of chaotic bifurcations, right? You have continuity dependence on initial data, it's true, but the time for which you have the dependence depends on the size of epsilon. So as epsilon goes to zero, it's longer and longer time, but the topological character of it suddenly shifts when epsilon equals zero.
Well, I can say that if you have small but finite delta epsilon, yes, for any small but finite delta epsilon, you will have an infinite number of reconstructions of this trajectory in the plane orthogonal to B. Yes, the density of these reconstructions will be smaller and smaller for delta epsilon going to zero, yes, but still you will have the finite density of reconstructions for any non-zero delta epsilon, because this trajectory is constructed in such a way that there are always points where it comes to itself very closely. It does not intersect itself in any point, yes, but there are always points on the plane, they are very far from each other, where it comes to itself closer and closer and closer and closer, yes, but you cannot organize, how to say, the convergent sequence from these points, but these points exist. So actually, for delta epsilon small but finite, you will always have a reconstructed trajectory, and this reconstructed trajectory will represent a set of compact trajectories. But these compact trajectories will be very, very long, and the length of these trajectories depends on delta epsilon, yes, going to infinity, delta epsilon goes to
If you think of this as a curve in p space, which it is,
in p space.
imagine it uniformly traversed in time. Does the curve x and y components have a continuous spectrum or a discrete spectrum or a quasi-continuous?
If you consider, for example, the quasi-classical quantization in this picture,
No, just as a curve. Just imagine to see if it's chaotic or not. I mean, is it take the x and y components of this curve, for example, as a function of arc length, say, does it and take the Fourier transform? Does it have a continuous or discrete? Because that's another way
it is a
of characterizing chaos.
it is a quasi-periodic curve. So this means the quasi-periodic curve, but it is not periodic. It has 3 quasi-periods. Yes, this means that its Fourier transformation will be a lattice, but everywhere dense lattice. Yes, it is not continuous. It is delta functions, but delta functions you have a
Discrete.
yes.
Discrete.
So it wouldn't have a positive Lyapunov exponent.
No, I
So
mean,
that's the difference between topological chaos and dynamical chaos, isn't it?
it is dynamically chaotic, yes. I told that according to the terminology of theory of integrable systems, yes, if the trajectory covers something like 2-dimensional to right, we will call it topologically integrable, topologically regular. If it covers something more complicated, the surface of genus more than 2, then in this case we'll call it chaotic, just using the terminology of integrable systems actually. Yes, but now,
Sorry, do I understand correctly? Because normally I imagine the system when integrability is special and any perturbation introduces chaos. And are you saying that it's the other way around? It's chaotic
Yes.
for delta epsilon equals
Yes.
0,
Yes.
and any perturbation makes it regular.
Yes, because yes, this was called topological integrability because the system is very special. Very special. Actually, you know, what does it mean, integrable or non-integrable? Where? Yes, the measure of set. This depends which kind of perturbations you consider. Yes, you cannot say that this system is integrable. You can have both situations: chaotic trajectories, chaotic cases, and topologically regular cases. And actually, this depends not on the system but on the space of parameters, how you change your system. And actually, these special deformations of system, this means that why it is so. I would say this is because the deformation of the system is rather specific. You always deform the direction of B or the energy level in such a way that the sets of closed trajectories are actually locally stable. So on the Fermi surface, except these open trajectories, you can have closed trajectories also, yes? And actually, these trajectories cut the Fermi surface on something which is simpler than the Fermi surface itself, yes? And the deformations are constructed in such a way that these sets of closed trajectories are stable. So because of this specific type of perturbation of the system, we could, yes, because if you deform, then usually closed trajectory disappear. Yes, but here it is deformed in such a way that. And now, what is the most important about these trajectories? I want to say now. First of all, its contribution to the conductivity. This contribution is very different from both closed trajectories and topologically regular trajectories because of very complicated behavior of this trajectory. So there is conductivity tensor written here for this type of trajectory. What can you say first? First of all, it blocks the conductivity in the plane orthogonal to B. But we can see, and this is very unusual situation for example, for free particles, it blocks also the conductivity along the magnetic field. Because the trajectory is rather complicated, and actually, again, from topological point of view, it covers a surface which is homological to 0. And this means, if you look at this trajectory, yes, the mean, the average of any Vx or Vy is the components of the group velocity in the plane orthogonal to B are 0. Are zeros for this trajectory. But what is important, if you take the average of the Vz of the component of group velocity along B, it is also 0 for this trajectory. And because of that, actually, this trajectory does not give any contribution in the conductivity along B. So this is very interesting fact for this type of trajectories. And if you find this trajectory experimentally, you can observe this, how to say, suppression of the conductivity along the magnetic field also. Usually these trajectories can exist with compact trajectories also. So there's, I mean, for generic Fermi surfaces, there still will be some conductivity along B, but in this case, you are going to have, how to say, sharp suppression of the conductivity along B, just for the corresponding directions of B on the unit sphere. Yes.
So, but you said this is very non-generic zero-measure phenomenon. It exists.
Yes. If you consider the generic Fermi surface, then the measure of directions of B on this unit sphere will be 0. But for specially made, yes, for specially chosen directions of B, you can still have these trajectories on the Fermi surface, and there are theorems of existing theorems. Well, let me now just 2 minutes say it is not connected with normal metals anymore, but gives a good picture from mathematical point of view of the picture arising in this situation. First, let us now consider, the question was actually, let us now consider not just the Fermi surface, which is given by epsilon of P equals epsilon Fermi, yes, but consider just the whole dispersion relation on the three-dimensional torus and consider all possible trajectories in all possible levels, epsilon of P equals constant. Yes, it is easy to see that, for example, first of all, epsilon of P is a bounded function. It has a minimal value. Its minimum value on the three-dimensional torus has its maximal value. So if you are very close to, for example, to the minimal value, yes, the Fermi surfaces will be very simple. They will be just small spheres, yes. Or if you go to the very close to maximal value, also Fermi surfaces will be very simple. They are all, again, small surfaces. Electron trajectories on these surfaces will be of different type. Electron type trajectories and hole type trajectories, yes. So, first of all, will you have open trajectories or not? First fact, for any direction of B, you are going to have open trajectories, or maybe a net of singular trajectories for some rational directions of B. You can have singular trajectories at one energy level for some directions of B. But generically, I mean, for example, for irrational directions of B, you are going to have always open trajectories, at least at one energy level. Generically, you have open trajectories in some connected energy interval. So you have, for given direction of B, some minimal epsilon 1 of B and maximal epsilon 2 of B values of energy, such that inside this interval you have open trajectories, and outside this interval you have only closed trajectories. So another fact, if you have a generic situation, if your interval is not zero, if it is not just 1 point, you will always have topologically regular open trajectories in this situation. And in the situation when the trajectories exist just on one energy level, you have both situations. If you're just on the boundary of the stability zone, you will have topologically regular trajectories, but for special directions of B, you will have these chaotic examples of Dimitrov type, very complicated trajectories with with the average velocity equal to 0, and all these phenomena. Yes. So if we consider the angular diagram, this is very schematically, for the whole dispersion relation, yes, it will be very complicated. There will be no regions here anymore where you have just open trajectories. Because for the whole dispersion relation, you cannot have this situation. For any direction of B, at least at one energy level, you have an open trajectory. So actually, there is a theorem. Maybe one sphere, in this case, is just one stability zone. This is one generic situation. Another situation, if it is not so, then you have an infinite number of stability zones on the sphere with the increasing topological numbers. And also you will have in this situation Tsarev, this theorem, you will have Tsarev chaotic examples, you will have Dimitrov chaotic examples, so all possible situations will arise. But if you, for example, go now to a metal, yes, and consider metal conductivity, you have to, how to say, to cut this picture. You have to take just the structures of this picture. For this, Fermi energy belongs to the interval. For every fixed direction of B, you take the corresponding structure of this picture if the Fermi energy is inside the corresponding interval of open trajectories, which depends on B, yes, and you say, okay, or either I have just closed trajectories if it appears that the Fermi energy is outside this energy interval. Yes. So this is interesting that actually first the angular diagrams which arise on different energy levels, they do not compete with each other. So you can make just one diagram for the whole dispersion relation, and that actually that it's more reasonable. I mean, and the situation becomes more clear if you consider the whole dispersion relation instead of just one energy level. Yes. So I think my time is over. Thank you very much. It's just what I wanted to say.
These are questions. So, maybe.
Well, actually, I think Phil may have tried to answer this or answer it already. But let me try again because I just want to hear whether I understand. So in R3, besides triply periodic surfaces like this, there are often these quasi-periodic surfaces. Sometimes they're levels. I guess you can always make them levels.
Surfaces are always periodic.
I know yours
Trajectories are quasi-periodic.
But I'm going to ask you a different question. That's what I'm asking. So the question is, there are surfaces that are quasi-periodic in the sense that they really periodic with respect to a higher dimensional lattice that either you slice or project down to R3. It seems like what you're doing with taking then these various slices, it would extend to that setting. Because again, I'm looking at.
Excuse me, if I understand, you want to consider the quasi-periodic surface.
Yeah, and there are many interesting examples of those that.
I don't know. I don't know. Well, first of all, from physical point of view, I don't know how it can appear, the quasi-periodic surface. For what?
There are all kinds of quasi-crystalline structures.
The electron spectrum in quasi-crystal is much more complicated. It cannot be.
What if more than 3 quasi-periods? 5 quasi-periods?
This is actually the general Novikov problem. Just describe the topology of level surfaces for quasi-periodic, for a quasi-periodic function with arbitrary number of quasi-periods. For 4 quasi-periods, there is a theorem of Dynnikov and Novikov. They proved the analog of Zorich theorem for 4 quasi-periods. What does it mean? That if you have a 2-dimensional plane in the 4-dimensional space and it is rational, yes, then for small rotations of the plane, you will have topologically regular trajectories. But nobody says that the measure of the directions of this plane is equal to 0 anymore in the case of 4 quasi-periods. If you consider 5 quasi-periods or more, then numerical investigations show that typically you have chaotic behavior.
Is it possible to consider this theory applied to superconductivity material?
Well, for superconductors, you don't have Fermi surface,
and
you don't have quasi-classical electron trajectories.
but Fermi surface.
Well, it exists, yes, but no quasi-classical electron trajectories, and rather big magnetic field should destroy this superconductivity.
So this, I mean, only with this behavior of curves on this.
I don't know if somebody discussed some quasi-classical motion in this situation. I don't know.
There are alloys, for example.
Alloys?
Alloys.
Well,
It's, yeah.
Well, alloys, they can be considered maybe like, but I mean, mean free electron time is rather small, yes, in these materials. So actually, from practical point of view, you are going to have a pure metal, yes, monocrystallic metal, which is very purified, yes.
What you asked, Misha, it's life beyond this picture, semi-classical, non-interaction particles. Of course, there are huge life there.
Yes.
Can you show us an explicit form of the dispersion relation for some real situation, some particular metal? What does it look like?
Well, any 3 periodic function, because there are, if you ask about analytical Fermi surfaces, there are different analytical approaches how to calculate approximately
Give me an example
well,
where you have done the calculation.
for example,
Binding Hamiltonian, you
well, for example, you can, yes, you can try to you can try to expand the Fermi the dispersion relation is in Fourier series. Yes, you can say that this, for example, if you have cubic lattice, yes, this will be first of all this famous dispersion relation. Yes. Plus and so on, yes. And after that, if you take different parts of this more and more and more and more, you have more and more analytical examples with parameters. Actually, Lifshitz, Asbel, Kaganov, Pishansky, they considered maybe 5 parametric Fermi surfaces. These plus, say, alpha cosine px cosine py, plus and so on. And they also made some results. From analytical point of view,
Your B is in, say, the Z direction here.
no, there is no B here. You asked just about the dispersion relation. Yes?
So is it isotropic?
It is not isotropic, cubic
Cubic lattice.
cubic.
you
For
might apply
example.
B in any direction.
Yeah.
So there are many analytical methods how to calculate approximately the Fermi surfaces, and according to these methods, there are many analytical approximate formulas for Fermi surfaces.
Yeah.
But for real, you usually measure the Fermi surface with the aid of cyclotron resonance. Other after that, use maybe maybe interpolating formulas or stuff like this.
Can you give us, in one sentence, something of the argument underlying those relations that you showed us, those calculations relating the Fermi surface to the conductivity? Is it, I mean, is it a long and complicated calculation, or
Well,
how the geometry impinges?
No, first of all, if you consider the Fermi surface in the magnetic field, yes?
Yeah.
The Fermi surface, what is the Fermi surface? This means that all the electron states under the Fermi surface are occupied, yes? And all the electron states above the Fermi surface are empty. Yes, and this is the state which current equals to 0, yes? What is going on if you switch on the strong magnetic field? You will have some, for example, quasi-classical dynamics on the Fermi surface, but still no current exists. Yes, because it does not change the distribution function. It is a dynamics on the Fermi surface, but the distribution function does not change it here. If you consider the electric field, then electric field, it changes the distribution function. Yes, for example, if you have a sphere, yes, if you have a sphere, then if you apply the electric field, then you can approximately say that the sphere is shifted. Now all the states are occupied inside the new sphere, empty outside the sphere, and this is a situation when you have non-zero current. This is proportional, the shift is proportional to electric field, and the inverse proportional to the mean free time of electron, and so on and so on and so on. But if you consider the electric field in the presence of magnetic field, you have different situation. Then magnetic field is rather strong. Electric field tries to shift the Fermi surface, for example. Yes? But magnetic field says, no, I don't allow you, because if you put some more particles here, yes, I will very quickly put them here according to the quasi-classical dynamics. So, but here there is no problem. If you want to shift a node B in this situation, you can. Yes? If you have more complicated situation, yes, then when you have more complicated Fermi surfaces, then the geometry topology of the trajectories works in more or less the same way. So this means what? For example, if you have topologically regular trajectories, they always appear in pairs. Yes. The trajectory, there is trajectory going to an opposite direction. If you switch the electric field like this, yes, then nothing happens actually, because particles do not acquire energy on this trajectory. But for example, if you switch energy like this, yes, then this means that here particles will acquire energy, and here particles will lose energy. And this means that here the number of particles here will be increased, and here it will be decreased because.
I understand this, and of course these are special cases. But what I was really meaning is there a general formula relating the quasi-classical trajectories to the conductivity emerging from considerations like this, of which the cases you showed are special cases?
Well,
with the different
first of all,
behaviors in
this is all the cases. Yes, if you want, for example, in tau approximation, a general formula, you can use, for example, the following formula. You can take the integral of the Fermi surfaces as Fermi, and after that, for any trajectory, for any point of trajectory, you can introduce, for example, the following value in tau approximation. So if you consider the point P, yes, for any point P, you can consider, for example, W of P, which is the following. You consider the trajectory that's coming to the point P, and you consider the average of the group velocity, the group of P of t of minus infinity to 0, yes, P of t e to the time minus t over tau, yes, something like this. And after that you integrate over the sphere this V group IWJ of P, yes, okay, D to S over like something like this, yes.
Okay, that's what I was wondering. Thank you.
And this value will be very different for different types of trajectories.
Yeah, I understand. Thank you.
So thank you very much.